Thank you. Thanks a lot to the organizers for giving me this opportunity to speak here. And also thanks a lot to the scientific committee. So as the title says, I will be talking about the Hodge conjecture for singular varieties. So I think it is safe to assume that everybody does know the classical Hodge conjecture, right? So, but okay, so I have already said this to some people, but if you cannot read my handwriting, please let me know. Okay, also I'm always over C. So suppose I have X to be a smooth projective variety. I know by Hodge's theorem that this will admit a pure Hodge structure. And okay, first maybe I say this. Suppose let CP denote the 3 abelian group of formal linear combinations of irreducible codimension P subvarieties of X. Okay, so we can have this, and we have that X is a smooth projective variety over C, so it admits a pure Hodge structure. The cycle class map goes from CPX to H2P XQ, and it takes say a subvariety V to its fundamental class. Okay. Now, I say that it is easy to show. So maybe I should. CP. Okay. It is easy to show that the image of the cycle class map is contained in H2P Q intersect with HPP C. So here I have the pure Hodge structure, so that means it's equivalent to having the decomposition. So I can intersect, and I can show that the image of CP, so sometimes I'll be a bit sloppy and I'll drop the P, but you know what I mean, is contained in this for an EP. And the Hodge conjecture, and maybe to be more accurate, I can tensor here with Q. Okay, sorry. I should have done that. So the Hodge conjecture asks whether the other way around is true. That is to say, so these are the Hodge classes, which I will denote by H2P Hodge X. Okay. And the Hodge conjecture asks whether the converse is true, meaning in other words that if I have a rational PP class, does it come from a formal linear combination of this irreducible codimension P subvarieties? Okay, so it's a well-known conjecture, and we know that it is unsolved, but there are certain varieties for which it is known. So I am I work mainly in the in moduli spaces of bundles over curves. So mainly those are the kind of examples I'm usually interested in. So I know there are many other examples where it has been shown. Okay, so let X be a smooth, projective, very general curve. And just for convenience, I'll say of genus G greater than or equal to 2. Okay. Then, so I will abbreviate the Hodge conjecture as HC. Then the Hodge conjecture is satisfied by 1. So by very general, just to be clear, I mean that if I look at the space of all curves, MG, and I remove countably many proper closed subsets, the things that are remaining are very general. Okay? So then the simplest moduli space of sheaves that I know is the degree 0 line bundles on the curve. So Jack-X, the Jacobian, satisfies the Hodge conjecture. And I do not know, unfortunately, who this was.
Could you please repeat the definition of very general again?
Yes. So I look at in general. Okay, so I should not say in general. So normally, when we use the word general, we mean that if we look at a space, let's say the space of curves here, we remove finitely many closed subsets. The things that are in the complement are general. When we say very general, we mean that not just finitely many, but countably many proper closed subsets, the things that are remaining, are very general. Okay? And this is, thank you for pointing out, this is actually an important condition. So the thing is that, as far as I know, and there are experts in the room, this is not known still for a not very general curve. So for an arbitrary curve, I think it is still not known whether the Jacobian satisfies the Hodge conjecture. So this condition of being very general is very important, and it is, so the proof is in Birkenhagen-Lange, and I cannot say too much about the proof, it's quite a long proof and I have a lot of things to cover, but basically they really need this condition of being very general. So what you do is that you show in this case that okay, so you know that you have Lefschetz 1-1, so the Hodge conjecture is satisfied in degree 1. So what you do here is that you show that the Hodge ring is actually generated in degree 1, and then you show that it is actually generated by the theta divisor. So the Jacobian is an abelian variety, and this proof kind of also works for any abelian variety. I mean, very general, okay? And so somewhere in the proof, you need to throw out a lot of curves for which this doesn't hold. And so that's why the curves that are remaining are very general. Okay, thank you. And the second one, so is, as I said, I'm a moduli spaces person, is that if I look at let's call this odd degree. Okay, so if I look at the moduli space of stable rank 2 vector bundles on X with determinant L, then this also satisfies the Hodge conjecture. Okay, and this one was proven by Balaji, King, Newstead. And I will come back to this later on. That's why I'm giving you these examples. Okay, so again here they use the fact that it is already known for the Jacobian of a curve, so this condition of being very general gets carried forward. So their proof really uses this one. Okay. I should use, sorry. Okay, so I hope things are clear so far. So I have a very simple question. So this all was done for the case when x was smooth projective. What happens if x is singular? So this is part B. Apologize for the handwriting. So what happens if x is singular? So if I want a formulation of the Hodge conjecture for when x is singular, just looking at the board, that means I need the left-hand side, I need the right-hand side, and I need the map, right? So this is what I have. Okay, sorry, apologize. So sometimes, I mean, this is what's mainly done in the literature, is that you can also go to the Chow group, which is that you have your CPX modeled out by rational equivalence. Okay, and the map here, I know this is very bad, but this map is called CP. Okay, so I have so what happens is that normally, if x is not smooth, the normal Chow group that I have does not work. Okay, because it does not work well with arbitrary pullbacks. So you need things to be smooth. But I have something that works for singular varieties, namely the operational Chow group. Okay, so that is the normal Chow group, and this as well I will just denote by APX. Okay, the second thing I needed was this Hodge structure. So the Hodge structure is not going to be pure because things are not smooth, but I do have a Hodge structure nonetheless, mixed Hodge structure. Okay, and Claude also mentioned this in his talk this morning, mixed Hodge structure. So I'm assuming people are a bit familiar with this. Okay, so I have a mixed Hodge structure. On here. The mixed Hodge structure, I have not just the Hodge filtration, but also the weight filtration. Okay, and I have the weight filtration, and then I have a Hodge filtration on the graded pieces. On the quotients. So okay, so what then I also have, so so that means I have the left hand side, I have the right hand side. I also have, thanks to the work of so this I think this is Fulton McPherson, so maybe I should write down names, but if I don't, I apologize. It's just that I'm not always sure about who to attribute things to, but I think this is Fulton McPherson. And then we have the okay, so no, I think this goes this way. We have the cycle class map by Bloch, Gilles, Soulet. And this I will just write as CLP. And here what we have is that we have our keep messing the notation up. Okay. And the litmus test for a good definition is that when you are, you reduce things back to what you know, you get what you know. So this is really a good definition, because when X is non-singular, the operational Chow group is just the normal Chow group. When X is again non-singular, this is just going to be your normal cycle class map. So here actually, before this, maybe I should ask you to do something. So if you find this talk extremely boring, this is a small exercise you can attempt. So you see that here we have it to this graded piece, right? So maybe you can try to see how to extend CLP. Okay? That would be a good exercise. All right. So now, yeah, maybe I use this.
That for the notation, is the range of W from P to 2P, or
From
the range of the weight filtration is conventionally P to 2P here, or?
Yes. Yes. Okay. No, it's not extendable. But I wanted you to try this instead of falling asleep.
So the exercise is also like extended, but
Yes, but it's to make you just think and think. So no, I didn't want to give you the answer. I wanted to make it seem like it is extendable, so you keep thinking. Okay. So this I abbreviate as SHC. No, it is not extendable, and there is actually a counterexample by Totaro. So, but we can discuss. But you should try. You should try. So, I mean, who knows? So, for all P, I ask that the image of CLP is going to be, again, GRW2P XQ, and I intersect this with the filtration that I have. So this, I have the Hodge filtration. So okay. So this is what I would refer to as the singular Hodge conjecture. So I ask that this be satisfied. Now, as I said, if X is non-singular, singular Hodge conjecture is equal to the Hodge conjecture. Okay? Okay. So the goal of my talk is to give a criterion for when SSP is satisfied. Okay? Yes, 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 sorry. Thank you. Okay, so it's exactly what you imagined. Thank you. Okay, so this is, so I hope that the goal is clear. Okay. Yes.
The relation between the two Hodge conjectures is not so clear. So could it be that one is true but not the other?
Okay, so if the Hodge conjecture is true, then the singular Hodge conjecture is true, not the other way around.
And the other way?
So I think if things were okay, maybe for now you just say, put it like this. This is clear? Yeah, so the singular Hodge conjecture is not stronger than the Hodge conjecture. It's just that when things are smooth, you don't really have a weight filtration. I mean, you can take the trivial mixed Hodge structure or whatever, and you will reduce things back to what you had before.
But it could be honestly weaker.
Pardon?
It could be honestly weaker.
The singular Hodge conjecture is in general weaker, yes. Yes, in general, the singular Hodge conjecture is weaker. So the point is that as far as I know, that there isn't a cohomological notion. I mean, there isn't a cohomological formulation for the Hodge conjecture when the variety is singular, other than really this. This is, I mean, what I understand. So there is some homological version by Janssen, which is also not proven. And this, if you think about it, if you know that, this is kind of the cohomological counterpart of that. Okay, so, but that is also not proven. So this is actually, in some sense, I think that this Bloch-Gillet-Soulet map is the most logical thing you can think of. You know that there is a pure Hodge structure floating around with this on the graded pieces. So you first try to get a map to that.
I'm sorry, I didn't understand something stupid. Like the smooth case of this is just Hodge conjecture, yes?
Yes.
So this means that if singular is true, then the smooth must be true. Yes, it should be the implication the other way.
Ah, sorry. Okay, so maybe we can discuss this a bit later. See which one is true. Okay. So how much time do I have? 40 minutes, right? So 10 past. Okay. Okay, so last week I gave this talk somewhere, and I went terribly out of time, and the audience was very happy, I was very happy, but the chair was very, very unhappy. So, no, seriously, they were very unhappy. So, okay, so, but anyway, if there are questions, you can stop me. It's, I mean, we will just, I mean, I will cut down. I mean, this is a good thing about giving a board talk, is that I don't actually have to finish. If there are too many questions, I just stop. But if it is a slide talk, then I feel compelled to keep going, you know. Okay, okay, sorry. So I will write this down because I do not want to erase this. So let I going from, so this is the open disk, the unit disk. This be a flat projective, and I write here the word nice, okay, because I will tell you what should come here, or rather you will tell me what should come here after I've finished explaining. So family with central fiber chi0. Simple normal Clausius divisor. I assume the following, okay? So this is the assumption. Assume x02, which is the union, maybe I can just write it here. xj, so this is union of intersection of any two components of chi0. So sometimes it will become x0, but you know what it means. Satisfies the Hodge conjecture. So this is first This is one assumption. And the second assumption is that a very general fiber of this family satisfies the Hodge conjecture. Okay. Then chi 0 satisfies singular Hodge conjecture. Okay, so everything there should be understandable other than the word nice, and I'm going to explain that, or you're going to tell me what should come instead of nice. Okay.
Sorry, what's the first point? X naught.
Yeah. So if I have a family where it's like this or whatever, and x naught is like this.
Okay, and X naught bracket 2.
Yes, x naught 2. That means the union of intersection of any two components. Okay, so these here, here, here should satisfy the Hodge conjecture. So this seems like a very maybe arbitrary thing, and you're wondering what kind of varieties will satisfy this. Well, I do have example of varieties that will have this condition. Okay, and maybe that's what I should mention. So if I look at the and I have so I'm being a bit so I'm going to not write all of this down. I'm just going to say it in words. So what happens is this. I told you in the beginning that we have the Hodge conjecture for the Jacobian and for the moduli space, right? So what I was doing before this is that I was trying to understand what happens if I take a family of curves and it degenerates to an irreducible nodal curve, and then I consider the moduli space over this family, and I know that by Giesecker's moduli space, so there is a this is what it so this is the relative Giesecker moduli space. So I have a relative Giesecker moduli space which is flat, projective, everything on the, and it is smooth on the punctured disk. So I wanted to know whether I can the result I showed you earlier, the Balaji King Newstead, whether I can get this kind of result for the singular fiber. Okay, so this is what, and this we already did, me and Ananya. And what happened is that we did this, and I was giving a talk, and Professor Simpson was in the audience, and he asked me later on, I also gave a sketch of the proof as to why this is not more general than it's just for moduli spaces. And I didn't really have an answer. It's just that I just knew moduli spaces, and I just worked that out. So, and then I thought that, okay, maybe this is, and my collaborator was also there. So then we decided to basically try to come up with a more general formulation and see if we can generalize this example. Okay, so the question of whether there is a concrete example which satisfies this thing. Yes, this is, in fact, this theorem is a way of coming from this concrete example to a generalization. Okay, and then in the process we learned a few things. One is that So the rough idea of the proof of this thing was to basically, you know, that if you have a family and you have this compact Kähler manifolds, and then you have already a apparatus to understand what happens to the mixed Hodge structure as the manifold degenerates. It's called limit mixed Hodge structures. Okay. So what we were trying to do was to basically connect the cohomology, the Hodge structure that we have on the singular fiber with that of the family, and to try to understand, because we already know it for the smooth fiber, we try to get that information for the singular fiber. So this is roughly the idea, but then things happen. So, okay, so I needed a whole board for this. So the key idea is to use the info about the general fiber. Okay? And so I have this punctured disk. So I have removed the central fiber, which is singular. And I know that I can take a covering of the punctured disk with the upper half plane. Okay, and here I have take the fiber product. Okay, and I have, let's say, point S in here, and over S I have chi S. Okay, and this is given by the exponential map. So I take the S here, and it goes to the ES is E2 pi I S. Okay. Okay. So now here this is a smooth family, right? So by Ehresmann's theorem, I have H to P. So I did not tell you. So this fiber product here, I denote by chi infinity. Okay. So this is the family. I have this is isomorphic to H2P chi ES here. ES just being the image of S, okay, and the fiber over that. I know by Ehresmann's theorem that this is isomorphic, but this is not a morphism of mixed Hodge structures. Okay. So my question is this, which maybe I should first tell you. Okay, so I equip H and Q. So we can equip this with Schmidt's limit mixed Hodge structure. So that is going to just be H2P where this filtration, the F upper dot, is given as follows. Okay. I mean, I can also have the monodromy operator. Okay, and n2 equal to minus 1 over 2 pi I log t. So I have Fp of H2P to be the limit of e to the 2 pi I s n, n is being the log of the monodromy operator, Js star pull back F P, HP. I think it should be, yeah. Okay, so sorry. So basically, I already have a Hodge filtration here, right? So I can try to pull that Hodge filtration back to this, and then I take the limit, and as the imaginary of S tends to infinity, I define the Hodge filtration on the limit. Okay, so how do I define the Hodge classes? I define the Hodge classes as exactly what you would imagine. I take the HPP intersect H2P TQ, which is going to be H2P.
You're taking limits as inmates of S goes to infinity.
Imaginary part of S. So we have the, this is a, so S was in the upper half plane, no? Okay.
You assume that the monodrome is unipotent?
Yes, yes, yes. Thank you. Absolutely. I assume that, and so I think for the experts, I really don't need to write this, but I wanted to write this, and I will ask you something at some point. So this intersect H2P infinity Q. Okay. Okay, so this is, I hope, clear. So what is this? Maybe we can write it again here. This is limit as any part of S goes to infinity, exponent 2 pi I S n j. So there's a reason I'm doing this. It's although seeming quite tedious, but okay. Okay, so this is how I define the Hodge classes. So now my question is as follows. In here, I have H2P Hodge, right? And again, I have Hodge here. I had an isomorphism here. Do I have a phi S here? So, question. Phi S? Is the question clear? Okay. So, and this is where things get interesting. So basically, does there exist, so I know that I have this morphism, but do Hodge classes here necessarily go to Hodge classes here? Okay, so I have a an example. Maybe I should ask the audience, should it happen or not? Nobody's listening, so okay. Okay, so I let pi to be a smooth family of hypersurfaces in P2n plus 1. Okay? And I ask that chi 0, suppose chi 0 lies in the Noether Lefschetz locus. So this would imply that the rank of H2P Hodge chi 0 is greater than or equal to 2, and I ask that chi s does not lie in Noether-Lifshitz locus. Okay. So, rank of H2P Hodge chi 0 is equal to 1. Okay. So, if this happens, then clearly there cannot be a map. So, there exists gamma in H2P Hodge such that gamma is not in. So, I am being a bit sloppy. Sometimes I write S and sometimes I write ES, but you should understand. Okay, so why would this be? Why would something like this happen? I mean, what is this precisely saying? This is saying that the Hodge lattice, the rank of the Hodge lattice can jump. Okay, so if the rank of the Hodge lattice can jump, there are going to be things here that don't have anything to go to.
So it's just because how does your theorem apply to this setup?
It's coming.
Okay.
So, 1 minute? No. Okay. Okay. See, I knew this was going to happen. Okay, so. Okay, so basically what I'm trying to say is that this will contain the limit s 2 pi I s n of see okay, so maybe I talk rather than write. Okay, so what happens is that here I know that this limit is going to contain, in case it's not big enough, this. Okay, but it's not necessarily going to be equal. And that is because when I take the limit, the Hodge classes of the limit mixed Hodge structure can be more than the limit of the Hodge classes. This is essentially what I'm saying here. And if you look at the board carefully enough, you can spot why. Okay? So I make this definition. I call a family, so a family pi is Mumford-Tate when phi s, and phi s not for all of this, but for the monodromy invariant part exists. Okay? And so the condition I need here is to ask not just for smooth projective, but not for flat projective, because this can happen even if the family is completely smooth, like I showed in the example there. Okay, so it's not a question of the singularity of the fiber. Okay, so I would need, if you know Mumford-Tate groups, what I'm trying to say is that the Mumford-Tate group of this is still going to preserve the image of this. Okay, so I want the rank of the Mumford-Tate group to not jump, at least for the invariant part. I know that if I don't put this, then it may never happen. But I need this, and I know that this I can show explicitly that there are examples of Mumford-Tate families. And the question is, how do I show it in more generality? How do I produce more Mumford-Tate families in order to satisfy this theorem? Thank you. I'll stop.